plug it back into the shell balance, you will have dAc star second order differentiation of Ca by dz squared minus k triple prime Ca equal to 0. Okay? In the textbook, they'll try to change this equation into dimensionless form. Okay? So you have concentration, which has units. They will convert them into gamma. By definition, gamma is Ca over Ca0. Ca0 here is a concentration of A on the surface. Okay? Remember, right now our system is in liquid. So Ca0 is concentration of A in the liquid at the surface. So the ratio between concentration at any level divided by concentration at the surface is called gamma, capital gamma. It becomes dimensionless. And psi is ratio between C over L. L is the depth of your beaker. In this case, if you take differentiation, you will have dCa equal to Ca0 d gamma. Right? Take differentiation. This one is constant. You can take it out from differentiation. You get this equation. From this part, you have dz equal to L d psi. So from here, at the end, you have second order of dCa by dz squared. It should equal to d by dz of dCa by dz, right? This is definition of second order differentiation. dc itself is L d sine. So here is 1 over L d by d psi. Inside you have dCa, which is Ca0 d gamma over dc. C here is L d sine. So you combine them, take Ca0 and L, which both are constant, out from the differentiation. You have Ca0 over L squared, d square of gamma over d sine squared. Put it back into the differentiation. Then you have dAc star Ca0 over L square d square gamma by d psi squared minus k triple prime. Ca itself is Ca0 times gamma equal to 0. Then I'm going to take all of this together with this term. All right? Everything in parentheses here is constant. They are constant. we will take this and call it by new variable. This is called phi square. Phi itself, it has a name. It's called TU modulus. You took kinetics already, right? Did you pass kinetics? Yes, of course. Did you learn about TU modulus in kinetics? Someone would say TU modulus. Some people would say Tilly modulus. I don't know which one is correct. Have you seen this variable before? Yes? 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 No? Okay. TU modulus would appear whenever you have a system, whereas you have diffusion together with reaction. For example, if you have porous particles, suppose this is catalyst, a spherical catalyst, and it is porous. Okay? Reaction takes place on the surface of the catalyst. However, majority of the surface of the catalyst reside within the pores. Imagine sponge. You know sponge? The surface, the outer surface of the sponge is not much, but particular or specific surface area of the sponge relies within the sponge itself. So that area is the area inside the pores. Okay? So if you have reaction like reaction of species A, mostly A would go into the pores first. And then along the way, it would diffuse and react on the surface within the pores. Sometimes people would say it is very hard to imagine this and model them like our last examples that trying to spread the area to get flat area, and A comes down to the surface of the catalyst, react on the surface like this. Sometimes people say, let's consider everything on the particles here to be uniform particles, and looks like A diffused into the particles. Okay? So where in fact A is moving inside the pores, but they are imagine it like A diffused into the what does it call? Into the solid part. They're going to assume that the whole particle is a solid, but the solid itself, A diffused into the content of the solid. And along the way here, so they're going to take a model from porous particles, and A move into the pores, model them into solid particles, and then A diffuse into the solid content. All right? And along the way of the diffusion here, reaction takes place. So if you look in this picture, reaction is heterogeneous. It occurs on the surface, the real surface of the pores. But if you look at this picture, the reaction is took to be homogeneous. Homogeneous in the solid content. All right? Whenever you have homogeneous reaction together with diffusion, TU modulus usually appears. Do you understand? Any question? All right. So from our differential equation, can you solve it? It is second order ordinary differential equation. You should already learn how to solve it from Applied Math 1, probably Applied Math 1. The answer of that differential equation would be something like this. Do you know this? Do you know this and that? No? No? Do you know hyperbolic cosine? This is called hyperbolic cosine. This is hyperbolic sine. It's a function. You can write down hyperbolic cosine and hyperbolic sine as a function or exponential of e to the power of I think. I'm not sure. But it can be treated as if it is cosine, but it's not a simultaneous function. If you bring your calculator, that's supposed to be this sign appears in your calculator as well. You just think that this is just a function, another function. Okay? And hyperbolic cosine of 0 is equal to 1, just like regular cosine. And hyperbolic cosine of of 0 is 1, of pi over 2 or 90 degree is 0, just like regular cosine. All right, in this part you have two unknowns, C1 and C2. These two are integration constant. So we will need two boundary conditions. What is boundary conditions? Boundary conditions supposed to be located on the boundaries. First boundary that we have is at z equal to 0. When z equal to 0, that means psi itself is equal to 0. What do you have at the surface? Concentration of A is 0. Okay? From here, that means gamma is 1. If psi is 0, cosine, hyperbolic cosine of 0 is 1. And then, from here, if you apply, you have gamma, which is 1, equal to C1 times cosine, hyperbolic cosine of 0. And this one is 1. Plus C2, hyperbolic sine of 0, which is 0.